Have you ever looked up at the sky and wondered why it's blue? If you've spent any time at all outside, this shouldn't be a question that needs asking. And yet this is one of the great classic science questions that has been asked by kids for generations. It's also the basis for some incorrect assumptions that might lead to even more questions down the line. Like, if the sky is blue during the day, then why are sunsets orange? To get to the bottom of this, let's break down both phenomena. The sky appears blue during the day because of something called Rayleigh scattering. This is a type of elastic scattering where light bounces off particles that are much smaller than the wavelength of the light itself. This is different from other kinds of scattering, like Thomson scattering, which involves much larger particles. When light hits those large particles, it transfers momentum and energy to them, and the light changes in some way, either in wavelength or direction, or both. But with Rayleigh scattering, the particles are so small that they don't cause any change in the light. So why does the sky turn orange at sunset if Rayleigh scattering is still happening? Let's look at what's causing the sky to scatter light in the first place. The sun emits light that's pretty much white, but contains a spectrum of colors. When that light hits Earth's atmosphere, it collides with various gases, water droplets, and particles of dust. These are the particles that cause the light to scatter. Rayleigh scattering happens when the particles that light is bouncing off are much smaller than the wavelength of the light. Visible light has wavelengths ranging from about 400 to 700 nanometers. And the molecules in our atmosphere are much smaller than that, about a 10,000th of a nanometer across. That makes it really easy for light to bounce off these molecules, which is why the sky looks blue during the day. Blue light has a shorter wavelength than red light. So when the light from the sun hits the atmosphere, blue wavelengths get bounced around all over the place, while the redder wavelengths pass straight through. So during the day when the sun is high in the sky, we see blue everywhere. But there's another effect at play during sunrise and sunset, something called me-scattering. Me-scattering happens when particles are about the same size as the light waves they're interacting with. Water droplets suspended in the atmosphere are around 20 to 40 times bigger than the wavelengths of visible light. The light from the sun passes through more atmosphere and interacts with those water droplets. Because the droplets are big compared to the wavelengths of light, they scatter all the colors equally. That means we don't see blue skies at sunrise and sunset. Instead, we see a mix of all the colors that make white light. Now, if that were the whole story, then sunsets would just look white instead of orange. But there's an even more interesting phenomenon going on here. As the sun gets lower in the sky, its light passes through more atmosphere, and the blue wavelengths get scattered away entirely, leaving mostly reds and yellows. Also, when the sun is low in the sky, the light from the sun hits us at a steeper angle, which means we're seeing light that's undergone multiple bounces. Each bounce removes a little bit more blue light from the mix, until we're left with mostly oranges and reds. So if sunsets are actually a mix of all colors of light, why do they appear so monochromatic? Why do they look orange rather than yellow or red? The reason comes down to how our eyes work. Our eyes have three types of color receptors: cones, which are sensitive to red, green, and blue light. When light hits those cones, they send signals to our brains that get processed into the color we see. Cones are most active when light hits them head-on. The more ophaxis the light hits the cones, the weaker the signal is. When the sun is high in the sky, the light is coming at us straight on. But at sunset and sunrise, the light takes a longer path through the atmosphere and hits our eyes at a steeper angle. Our eyes aren't great at detecting red light, so the red and orange hues look washed out. You know, there's more to the color than just red and orange, but we can't see it without extra help. To see the full range of colors in a sunset, you need special equipment like a spectrometer that splits light up into its component wavelengths. But there's something even simpler that will help too: a bit of clear plastic, like a CD case. When you hold it up to your eye, you'll see a ring of colors form around the sun. Those colors are the wavelengths of light that were scattered away from the sun, mostly blue and green. Without the CD to enhance our vision, we can't see those colors, but they're definitely there. It turns out the reason sunsets look orange rather than red is because our eyes are more sensitive to yellow than red. And the reason sunsets look even yellower than that is because of a quirk of physics called constructive interference. Constructive interference happens when two waves combine to make a larger wave. Let's say two waves of light are moving through space toward each other. At some points they'll line up perfectly, meaning the peaks of one wave match the peaks of the other wave. When that happens, The waves combine to make a bigger wave twice as tall as the original. This is constructive interference. In other places, the waves might line up such that the peak of one wave matches the trough of the other wave. When that happens, the waves cancel each other out and we get zero amplitude. This is called destructive interference. Constructive interference happens with light waves too. It can explain why certain colors look more intense at sunset than others. One explanation for why sunsets look yellow is that the water droplets in the atmosphere act like tiny little prisms, bending the light and separating it into rainbows. But that's only part of the story. Another piece of the puzzle is that when sunlight bounces off water droplets, it undergoes something called internal reflection. Some of the light bounces off the inside of the droplet like it's a mirror. This only happens with angles of incidence greater than the critical angle. And the critical angle is different for different colors because of a phenomenon called dispersion. Dispersion is what separates white light into a rainbow, because different colors of light bend at different angles as they pass through glass or water. This happens because each color has a slightly different wavelength, and each wavelength interacts with the molecules in the medium in a slightly different way. For red light, the critical angle of incidence in water is about 48 degrees. So that means any light rays hitting the surface of a water droplet at an angle greater than 48 degrees will undergo total internal reflection and bounce off the back of the droplet. The critical angle for blue light is less than half that, at about 23 degrees. So blue light is much more likely to undergo total internal reflection. And here's where things get interesting. Blue light that undergoes internal reflection before exiting the water droplet is canceled out by blue light that exits without being reflected. That's because the light waves interfere with each other. And they interfere constructively when they re-phase, and the same when they exit the droplet. The light waves that undergo internal reflection exit the droplet shifted in phase by 180 degrees. Remember, the light waves interfere and cancel each other out when the peak of one wave lines up with the trough of the other. So blue light, which is more likely to undergo internal reflection, ends up being canceled out. That means the light coming from water droplets at sunset is more red than blue, because the red light doesn't undergo as much internal reflection and cancellation. It's the same reason that sunsets look yellower than they should. Most of the yellow light undergoes internal reflection and constructive interference, making it look more intense. So not only does Rayleigh scattering play a role in making sunsets orange, neither does Mie scattering, but also the physics of light waves interfering with each other. It set a testament to the ingenuity of scientists that we were ever able to figure this stuff out. They didn't even have YouTube videos back then. But it also shows how complex the world can be sometimes. There are multiple factors contributing to a single observation, which is true of sunsets and also true of the world around us. Even simple questions like why is the sky blue can take a lot of effort to answer properly. So next time you look up at the sky, whether it's blue or orange, remember that it took thousands of years of scientific development to get to the point where we can answer why. And there's still so much more to learn. Thanks for watching this episode. And thanks especially to our patrons who help support this channel. We couldn't keep making these videos without you. And you too can help us keep making videos. Head over to our support page to learn more.